All right, everybody. Ildar, if you are with us, could you please share your screen again? Okay, so let me officially start the last session for today. We have two wonderful speakers left. The first one will be Ildar Farkhatdinov from Queen Mary University of London and also affiliated with Imperial College London. So while Ildar is setting up, let me just tell a couple things. So we've been friends with Ildar for many years now, and he finished his master's in South Korea and then PhD from one of the best universities in France, so Pierre Marie Curie. Correct me if I'm wrong, Ildar, that was your PhD, and then he was a postdoc in the Imperial College for several years, and now he's a faculty with the Queen Mary University of London. So Ildar is involved in research about teleoperation and human-robot interaction. And without any further ado, Ildar, you have the floor. Please go ahead.
Thank you. Do you hear me and do you see my screen?
Yes, everything seems fine.
Okay. Let me know if there are any issues with the sound or video, because in the morning I had an issue with my Wi-Fi. Hopefully it's fine now. Thank you for inviting. So I will speak mainly about what my team at Queen Mary is doing, plus I will start with my background research. So my team is called HAIR, Human Augmentation and Interactive Robotics. And here is my background. I'm originally from Russia. I did my undergraduate in Stankin University with Yuri Podurev, but then I got links with South Korea, where I met Igor. I was in a group of one of the keynotes to the Professor Ji-Hwan Ryu. In France, I've been working on human vestibular system and balancing in robotics with Vincent Haybert, Anna Miklaska from McGill University, and Alain Berthoz from Collège de France. And since 2013, I'm in London, where I was postdoc first at Imperial, working mainly on rehabilitation robotics. And for last 4 years, I have my own team at Queen Mary University of London. So university was established end of 19th century. It's a very much research-oriented university located in central and east London. We have 9 Nobel Prizes. We are ranked quite high in UK and globally for research achievements. So our Center for Robotics, which is a multi-faculty center, here you can see examples of research from key academics. So head of the center is Professor Kaspar Alsofer, who was for many years at King's before joining Queen Mary. So he works on soft robots and sensing technology. We have Laurent Soyamone working on cognitive robotics and tactile sensing. Ketao Zhang on mechanisms, reconfigurable robotics, and myself on assistive technologies. Here is my team. So mainly PhD students, one postdoc joining soon. You have a website here if you're interested more. So in terms of my research approach, I'm doing human-centered robotics. So I learn from humans to design bio-inspired robots for humans. And in this presentation today, I will talk on these 5 topics. Let's start with haptics for teleoperation. And we know when we teleoperate robots, we mainly rely on visual feedback from cameras. It's a classical approach. Of course, not always suitable, depending on the application. So when I was at Korea Tech with Professor Ryu and together with Professor Podurev from Stankin, we have been working on developing novel force feedback technologies and methods for displaying environment of a mobile robot, which is remotely controlled by a human operator. So, of course, it was not really novel, but what we introduced was a novel approach to take into account the state of the robot, in particular velocity relative to the dynamic environment. And we were able to run our experimental study in which a human operator on the left was controlling a mobile robot on the right. A robot was put in a narrow corridor, invisible to a human operator. Human operator was relying on a camera view and ultrasonic sensors around the robot to tell where the obstacles and where the moving dynamic environment is. These obstacles and environment was perceived by a human operator through force feedback device. So we compared conventional approach and our approach, and we found out that with the help of our approach, you can see on the right, these are trajectories of 5 trials from the same human operator. And the differences are quite clear. So our approach was more precise, more accurate, safer, and overall provided better performance for the teleoperation. So we got a Best Poster Award for this research at Haptic Symposium in 2010. So now what I do for telerobotics is together with my PhD student Joshua Brown, I'm developing soft haptic interfaces based on particle jamming. So we take a cavity, like you see here on the right, and we put small particles. This environment is sealed. We can control pressure inside. We can create negative pressure. But what is the novelty here is that we put a vibration actuator inside, which propagates vibration, mechanical acoustic waves to particles. And by controlling the pressure, we are able to modulate the speed and the physics of this waves propagation. When a human operator interacts with the interface through a soft, thin film, a human operator is able to perceive different physical touch sensations. So we can program different materials, we can program softness, renders, and even shape. The idea is that such interfaces can be useful for teleoperating robots which physically interact with their environments. For example, as you see on this figure, a robot overcoming an obstacle with the help of rubber wheels. So this information, physical information, can be helpful to a human operator. And we got a Best Paper finalist at recent Haptic Symposium. Together with my other student, Francesca Palermo, I'm looking into how tactile sensors can be used in telerobotics to explore mechanical fractures. This is done with collaboration within the framework of National Center for Nuclear Robotics, funded by UK government, together with Professor Kaspar Alsofer. So we have an optical sensor. Let me switch to pointer. So we have an optical sensor. It is composed of purely optical and optical fiber elements. It is safe to put this sensor in radiation, so signals are not affected by the radiation. And through observing how the optical waves are changing their intensity, we can detect cracks on the surfaces. We have combined tactile approach here on the right with a visual approach, such that a robot can first explore remote environment visually. After visual inspection is done, with the help of deep learning, we can identify areas of interest. Then we can send our robot to do a detailed exploration of these surfaces, where we can finally confirm if there is a crack or not. Here is a demonstration. So a sensor on the left and on the right has 2 areas of interest. On the right, we have a real crack. On the left, we have an photo of the crack. So with the help of fused visual and tactile modalities, we are able to achieve high classification results. So we can, with accuracy more than 90%, we can classify the surfaces which are cracked and not cracked. Next, I will introduce you my research, of course, in collaboration with the colleagues, on how can we develop robots to study humans. One typical way to study human neural system is to do fMRI. And robots, they cannot operate in fMRI environments because of extremely high magnetic fields. This is what you see an experiment to destroy an old MRI scanning machine with the help of a metal chair. You can see the force here is more than 1 kilonewton, because the chair is attracted by the core magnet of the machine. So if we put a robot inside, it will kill a human. Second issue is if we have any electromagnetic devices, we can interfere with the image, we can contaminate the scanning process. So we have proposed a haptic interface in which all key components are made of plastic and glass. This interface is operating for flexion of extension of a wrist joint. Wrist joint is a good part of a human body neural motor system to analyze, because it has a very simple muscle group which defines the motion for flexion and extension. So we place this interface next to the scanner, and all electromagnetic and ferromagnetic elements are placed more than 2 meters away, and they are driving our handle with the help of cable-driven actuation. This was done together with Professor Etienne Bourdet at Imperial College, and I forgot to mention our colleagues from King's College who are doing clinical side of this. The idea of this type of interface is that we can simultaneously look into 3 levels of physiological measurements. So we first look into human movement kinematics, second muscle activation, and at last brain activity. We have tested the system with human participants. Here you can see fMRI scans. This is actually my brain. So there is no contamination. When the device was working, we get clear images. Second, when the interface was on and when interface was off, for the same motor task, same wrist movement, we achieve very similar or statistically indifferent motion patterns in the brain. So neural correlates are same. It means our device does not introduce any motion artifacts, which is crucial for fMRI studies. So that was best paper finalist at World Haptics in 2015. And here you can see that the device can be packed in a shopping trolley and can be easily moved to a hospital by taxi or public transport, which is important for such interfaces, because hospital time to use the equipment is very expensive. We move on. This interface was recently developed also with colleagues from Imperial College London. It was mainly PhD of Xin Yun Huan. It's an interface, again, cable-driven, to measure biomechanics of human lower limbs, in particular knee and hip joint. We are interested to identify dynamical properties of these joints because they will help us to design user-specific wearable robots. Device is operated by extremely powerful DC motor, so we can achieve very fast and strong perturbations, which are faster than human reflexes controlled by a spinal cord. To give you an example, we can achieve up to 1000 Newton force within 50 milliseconds of time, as far as I remember. So here are results for hip dynamic parameters. In particular, stiffness is important for biomechanics. And this was the first time it was possible to measure experimentally hip joint stiffness because of the complexity of the joint, as well as the human hip is extremely strong, so the system for measurements should be highly dynamic. It was published recently in Transactions on Biomedical Engineering, and results of for hip measurements in Transactions on Neural Rehabilitation Engineering. Next topic is on how we can design robotics interfaces for virtual reality. This is a concept we have proposed within the framework of National Center for Nuclear Robotics in UK. The idea we have is that a human operator remotely controls a mobile robot equipped with sensors, cameras, and manipulators to inspect potentially dangerous waste. It can be nuclear waste, can be chemical waste, or can be simply debris with unknown stuff under it. Such systems are operated by professional trained operators, or we have to also use similar systems for training. Therefore, virtual reality can be especially helpful. So the environment can be recreated, the real environment can be reconstructed with the help of virtual environment. We can use computer vision techniques to read the labels, to understand what can be potentially harmful or potentially dangerous. Virtual control interface, virtual training assistant, and a detailed camera view if necessary. All of this can be implemented. My PhD student, Bukihano Marali, has contributed to this project by developing a VR-based manipulation interface. So a human operator, as you see here on the video, can control the end effector of the robot, as well as we can control independently joints of the robot by moving the virtual model. The real robot on the background is copying the motion of the virtual avatar. Force feedback can be provided through handheld devices, or if necessary, we can use stationary haptic interfaces within the same setup. Kinect cameras can be mounted on the robot or separately in the environment to provide visual representation of the environment. So this setup was tested for different type of grasping techniques, and we are working further on integrating sensing capabilities of the remotely controlled robot into the VR now. Currently, Buki is doing his internship in Italy, in University of Genova. Second topic I'm interested in virtual reality and robotics is spatial awareness. In many cases, visual information from onboard cameras from mobile robots is not sufficient. For example, here, robot is either climbing upstairs or climbing or descending downstairs. And for non-trained operator, it might be very difficult, especially for those who don't know the environment. And this can be the case if we go to a waste storage room, which was not open for 50 years because it was too dangerous. So maybe you can try to guess if it is up and down, but instead of guessing, we are suggesting to develop interfaces which can communicate such information with the help of verticality feedback and terrain feedback. With my PhD student Atta Ottaran, we developed a single degree of freedom ankle platform on which a user can put his or her feet. Platform can sense foot tapping to control robot or avatar movement. So it's like natural walking. We do left-right foot tapping. Platform automatically detects left-right movements and implements walking of the virtual avatar or a legged robot in the scene. But because the platform is actuated, we can program the DC motor to implement various terrains like ice, concrete, sand, or even water. So depending on the type of the virtual environment or the sensors we get from the legged robot, we can get different type of haptic feedback applied to human operator legs. And importantly, we can also produce slope feedback. To our knowledge, this is the first type of interface which can integrate all this functionality together in a single DOF system. Okay, here's a more detailed video for that. Here we demonstrate that we can use, because it is a lower body feedback only, we can use upper body hands to control avatars or robots upper body or manipulator functionality. Let's move on. Yes, this is our global view. So such interfaces can be used to control human-like robots or robots with wheels and upper body, or more like a human-like, or simply robot with multi-leg systems. Now, final topic for today is how we can use wearable robots to augment human balance and gait. This was a European project I was participating when I was at Imperial. Together with University of Twente, we used the Lopez exoskeleton and a treadmill. A human user was placed on a walking treadmill. A robot was transparent, and left and right pelvis perturbations were randomly applied. In that case, we programmed the exoskeleton to assist balance recovery with the stepping left or right when perturbation was detected. So when upper body was perturbed left, we had to, or right, we had to use corresponding leg to do lateral stepping motion. And we developed controller to detect this perturbation and to apply assistive torque when necessary. Here is an example of this assistive torque in blue, when the perturbation to the pelvis was applied in orange, and pelvis was moved laterally in yellow. So this assistive torque was energy-based, and it depended on the operator acceleration when the perturbation was applied and detected. So we have tested this in an experimental protocol with several participants. All were healthy. We did baseline when there was no robot. We did adaptation when there was 50 perturbations and 50 assistance torques applied, and catch trials when assistance was randomly removed at some point of the experiment. Visually, when we have no assistance, so transparent robot, and when we have assistance, a robot was applying assistive torque when perturbation was detected, it was hard to detect the differences. However, kinematic measurements and EMG response of the human users was showing significant changes. First of all, assistance, this is hip abduction angle, and red is assistance, blue is no assistance. So we can see red increases hip abduction. So we are increasing base of support of the walking process. Yellow is when we had assistance removed, but a user did not know about that. So yellow and blue are very similar, meaning that user did not really need to adapt back to non-assistive cases, which is important for assistive controllers. And EMG was reduced. So we had an EMG to measure gluteus medius muscle for hip abduction. EMG was significantly reduced in all participants when assistance was applied. And it's important to mention this is assistance control, it's not rehabilitation. That is why reduction in EMG is actually what we want to achieve here. Yeah, let me skip this because I don't have much time. So we have tested this with post-stroke patients. In particular, here you can see a trial with a female 71-year-old post-stroke survivor. Exactly same algorithm. We simply adjusted the scales the gains to produce less assistance because of the age of the patient and the medical condition. But we achieved similar results for patients as well. Now I will show you how we can use wearable haptics to assist mobility. So we worked with deaf-blind people who cannot see, people who cannot hear, and they have to use a sign language. Let me see if you have sound here. It's a small demonstration video. So yeah, let me chat. Okay, no sound. Unfortunately, I don't know what to do, but I will explain you. As you see, this lady, she is not deaf-blind, and this person is deaf-blind. This lady is using tactile sign language to ask a deaf-blind person whether he wants coffee or tea. And he confirms his answer by talking because they can talk, depending on their deafness condition. So they use tactile sign language, but touch for them is crucial to maintain this ability to communicate. In addition to sensory deficits, they often have other problems like speech, reduced mobility, autism, and they need rehabilitation techniques, rehabilitation therapy if they have autism. In UK, we have met a charity called Riding for the Disabled, where they organize therapy for autistic deaf-blind people. A person who is riding a horse here, he is deaf-blind, but also autistic. So he needs to do this therapy to maintain his mental health and well-being. However, as you see, he needs a tactile sign language interpreter. Not sure if it's not running, and a horse riding instructor. So this requires two people and it is expensive. They were asking us whether we can use haptics to optimize the process. It was done together with Imperial College London and Shadow Robot Company. So we simply proposed to have a smartphone application which will be controlling wearable bands with haptic vibrators to give commands to turn left, right, or to stop or to start movement. In that case, we only need one person who can be an instructor and therapist at the same time. Here you can see a demonstration before and after our system was introduced. So on the right is the same person after using our system. He can ride the horse without any physical support by therapist or a tactile sign interpreter. This significantly improves the quality of therapy and this specific person's well-being and health condition. This system has been deployed and been used for 5 years by this charity already. Finally, I have a new project starting next year to develop ergonomic support for supernumerary limbs which can be attached to a human body to support load carrying tasks. But interestingly, not much has been done in terms of developing balancing and back ergonomic support for supernumerary limbs. So I will have a postdoctoral researcher who will be looking into this problem for the next 3 years. And this is funded by UK government. I would like to thank Igor very much for inviting me. And I have PhD openings in my lab. So if you would like to join a great team and try great British beer and meet great British people, you're always welcome to contact me by email, and I'm happy to answer your questions.
Thank you very much, Ildar. So just to remind everyone, feel free to ask questions in the chat. And then for from my side, right? So you worked a lot on the lower limb support and then the verticalization of robots as well. So, for example, in terms of sensors, do you use entirely different sets of sensors for wearable robots and for humanoid robots when you support walking, for example, or are there some overlaps?
In general, when we speak about balancing problem, if you take a biological approach, humans, they can balance themselves with their vestibular system, and they use some other things like body proprioception and tactile feedback from the feet when they are standing. But it is always possible to remove tactile sensation. So if they are, let's say, flying in zero gravity, or if they are standing on something with a single point contact, like a platform for balancing with a single point contact. In that case, vestibular organ will be the only one they will rely. If we speak about robots in that sense, it is inertial measurement units. They rely on knowledge of gravitational acceleration and translational acceleration, so inertial forces, plus angular movements, angular rotations of the body they attach to. So these are the primary sensors we use. If we speak more on humanoid robots or wheeled legged mobile robots, they can also rely on vision and tactile sensing, or taking assumptions that we know that, for example, if we are in the building, the walls are vertical, the floor is flat, which is not always the case. So maybe this is an overview of the sensing capabilities. Yeah.
The reason I'm asking is because I remember a while ago you were also working on the autolytic sensors.
Yes.
Right, on the level.
Yeah,
so
that was my PhD topic, which I did not put in this presentation because it may take too long time to explain it properly. It was quite analytical, but the idea is that inertial sensors like accelerometers or inclinometers, they behave following Newton laws, and they state, and that is also Einstein's principle, we cannot distinguish between the source of acceleration, if it is accelerated body due to forces or due to gravity. So that is a primary, that is one of the main problems in inertial measurement systems. And we, in case of humans or animals, we have a thing called motion sickness. We can feel dizzy if we have conflict of information coming from different sensors, because our otoliths inside the vestibular system, they are not capable of separating these two types of acceleration. Yeah.
Thank you very much, Ildar.
Do you have
one question from the audience here? Let me read it out from Praveen Silvaraj. So, do you have any plans to extend your VR-based teleoperation system to use augmented reality? For example, demonstrating a grasp point for object to make it more user-friendly for for the user to interact in the virtual reality.
I did not specifically look into augmented reality because my primary application area was teleoperation. In that case, robot is in a remote environment. We cannot really touch the physical robot. That is when I think AR can be useful. Or we can touch a prototype or copy of the robot on the human operator side, but I didn't think really about that. But amount of research which has been done in AR-based learning by demonstration is quite a lot, so I decided not to. I prefer to start something which is less explored.
Got it. Thank you very much, Ildar, again for your talk and for your fascinating slides as well. So I'm afraid we're out of time. Thank you very much.